Conditional probability is one very key topic that requires a bit of some pragmatic thinking. So there are only two laws here that you need to know. Paper one, special paper one, is a pattern. A given B is equal to A intersection B over B. So guys, area panshi, you intersect the people there, the two letters. Now when you cross multiply these two guys, you find that A intersection B is going to give you the probability of A given B times the probability of what? Of B. So when you cross multiply, so what I'm trying to teach you is that if the base here is a multiplicand, automatically you're going to get an intersection. So you need to make them have simpler formulas that will help them remember. So even if you have to close your eyes, B given A, I just need to multiply this one by A to get the intersection of the two letters that are there, to be A intersection B. This formula is a prostitute in the sense that it has so many forms. You just need to know when to use it. You can also have A intersection B if you're not given any conditional probability by simply multiplying the probability of A itself and probability of B. You can only use this formula when you're only given these two available sets. But if there's A given B, this supersedes theorem 1. We know that A union B is given by the probability of A plus the probability of B minus the intersection of A intersection B. So this gives us a third formula for the intersection. We can put this one this side. We simply say A intersection B therefore will be equal to the probability of A plus the probability of B minus the union of A and B. So this is our fourth formula of what? Intersection. The fifth formula for intersection, when you have A intersection B, is simply probability of A, subtract the intersection of A and B. But if A is the one subtracting, the complement should be on the other letter. Lastly, A intersection B can also be probability of B minus the intersection of A and B. But if B is the one subtracting, the complement will be on the letter A. Sharper, these are the only formulas that probability can interchange with. Other than this, it's simply a condition to say that if A intersection B is equal to 0, it means they are mutually exclusive. There's nothing in common. It means they're disjoint. When you have sets A and B that don't meet anywhere. If you're dating a guy who you have nothing in common with, just say you and I are mutually exclusive, we don't meet, we don't intersect anywhere. It means they're mutually exclusive. So this is a condition. If we're given probability of A given B, if A given B still remains as A, it means they're independent, they're interdependent. It means A is independent of B. Okay, so A given R, if it still remains as A, means these guys below don't affect. It's like a lady, whether you give her money or not, she's not dependent on you, she still remains herself. That means they're what? Independent. A given B is still A. A given R is still A. Or B given what? A. For them to be independent, it still must remain to be what? B itself. So these are the only key rules under conditional probability that you need to know. The rest are simply questions that we're going to now sing about. So probability of A is 0.2, probability of B is 0.5. Can somebody give me how to find the intersection of A and B? What is the probability of A intersection B?
Yes.
Huh?
Look at probability of A given B, or probability of A and B, or probability of
It is simply just multiply probability of A times probability of what? Of B. Because F work the FBD. Intersection means what? You multiply. So probability of A intersection B, just multiply them. This is called theorem 1. All right? Taisa isa. But if you're given another, like A given B, is equal to what? 0.6. Then forget about this guy here. This rule will not hold. So to find A intersection B, I said, go for a conditional probability to create A. So we're given A given B. So I said you multiply it by the base. Guys multiply here. It will give you the intersection. So what are we going to have? 0.6 times 0.5 to get 0.3. I repeat, this answer is correct on condition that we don't have this guy. This guy has more power. Given these two guys, who should multiply, because intersection comes in forms of and the same as multiplying. Union comes in terms of or we add. So I brought in a new guy here. So that guy invalidates theorem 1. So number 12 money. All right. I'm Papa school modify. So please, these are theories of what? Dead men. You can't argue. So what is A union B?
You got probability of A plus probability of B minus probability of the intersection of A and B.
Excellent. So this is dependent on the answer we got. If we got the answer wrong here, na pakukasa. So our A is 0.2 here, our B is 0.5. The intersection we just found as 0.3. So when we calculate that, we get 0.4. Okay, please, I want everyone or anyone to at least say something. What is the complement of A? Anyone wasn't spoken?
One minus probability of A.
1 minus probability of A itself, correct. 1 minus 0.2. We have 0.8. Okay, who wants to try the complement of B? What is the complement of B?
One minus probability of B.
Yes, 1 minus probability of B. So our B was what? 0.5, meaning the complement of B will be 0.5 as well. The clue share up, please. I'll repeat where you are not clear. Anyone behind somewhere? Your husbands brag that you're doing a master's. They don't know your MBA idea. That is my secret to keep. Okay. So who wants to take us through A given B? How do we expand this?
The probability of A intersection B over probability of B.
Correct. So ngate mufo kulaba kutwala chili branch first hapa. B arise hapa. Then here we have A intersection what? B. So A intersection B not sanga kare. What is our A intersection B? A intersection B was 0.3 and our A was 0.2. Is it?
Yeah.
Is that so?
Yes.
Isn't it the beta that we're supposed to use there?
It's a B, yeah,
Probability
because
for
giving us a wrong figure. Here, A given B, A intersection B over B. So upper, our A intersection B is 0.3. And what is our B? Our B is 0.5.
0.5.
Thank you for that. I'm discharging you from BID. So what are we getting here? 0. What? 0.15. Right? Or 0.6.
0.6, yes.
0.6.
0.6.
Great. All right. Who wants to try what's the probability of B given A? What will go down?
Okay.
A. On top,
So
what are we going to have?
B intersection A.
Yes. So times A.
B intersection.
Okay.
Oh, they don't interchange.
It's the same thing. A intersection B, B intersection A. It's like 2 times 3 and
Okay.
3. Okay. Right together.
Okay.
Oh, it's the same thing.
Like 2 times 3 and 3 times 2. Okay. So these ones, that is how we do it. Okay. So who wants to try what is the probability of A given B complement? How do we do this? What comes down? B complement, right? And what is on top? A intersection what? B complement, correct.
Intersection.
So we know that B complement is what? 1 minus what? B. And our B was what? 0.5. Meaning we still get 0.5 there. Then A minus B complement. I said if the complement is on the B, meaning the subject should be A. So you say probability of A is equal to what? A intersection B plus A intersection B. But the complement should be on the other letter. Which letter? If there's A there, the complement should be on B. So what was our A? Our A was 0.2. Okay. So here you put 0.2. A complement intersection B. So here this is 0.3. Except that I didn't formulate the question properly. It's not supposed to give us a negative when it goes there. But this is a concept that you're supposed to get by. What I'm trying to head you towards is us answering this question here. Let's try this question, question number 18A. Is it possible for events A and B to be having a sample space? 7 marks. So the only way for us to know that a sample space exists is to ensure that our probability is not more than what? It's not more than 1. What's the probability of A union B? Probability of what? A
A
plus
B,
probability of B
probability of B
intersection,
minus what?
intersection of
probability
A
of
and
A intersection B.
Intersection. So this one must not be more than what? More than 1. What is our A? 0.5. What is our B? 0.8.
0.8.
So when we multiply this one, which of these two should we multiply to get an intersection to this one?
the A multiplied by the A given B. So we multiply the probability of B multiplied by A
A
given
given B.
B.
Multiply by what?
The probability of A,
Of A?
B has been given. So the B, we use the probability of A given B. We simply say we have the B. What is the probability of A? So we use B there.
Here we use B.
Yes.
Correct. So this one will give us the intersection of what? A intersection B. Once these two are the same, so this is why you appreciate what I was telling you. You can't put A there because this is not A. You put the letter which is there down there. So what is our A given B? 0.2. What is our A? 0.5. When you multiply this one, you get 0.1. So that's the one we're going to put here, minus 0.1. So when you add this plus that, minus that, what are we getting? .12. So does the sample space exist? No. Why? Because this one is more than 1. So this is the formula that you use to validate whether the sample space exists. Are we together? So here we're told that let A be the event that a microchip is manufactured perfectly, and let B be that the chip is inserted correctly. So A is manufactured perfectly, B is manufactured correctly. What is the probability that it is both functions perfectly? So what's the probability that it's installed and functions perfectly? So they're simply asking for the intersection of what? A intersection B. So who can help us find, how do you find A intersection B? Simply probability of A.
Multiply A and B.
Excellent. Just multiply A and B directly. When you get these two answers, you get your final answer. We are not given anything else. You multiply A and B. Lastly, there is what we call probability trees. You'd be given the probability of A at 0.4, probability of B at 0.6, and your total probability of D given A is 0.1, and probability of D given B is 0.04. So we're being asked to find 3 things. Number 1, the probability of D. Number 2, the probability of A given D. And number 3, the probability of B given D. So quickly, I'll teach you what is called a contingency table. To start with, there's what we call prior probabilities. These are called the original probabilities. The prior probabilities must always add up to 1. So the probability of A, what is the probability of A? 0.4. And probability of B?
0.6.
0.6. Are they adding up to 1? Yes.
Yes, sir.
Then we have what we call the conditional probabilities. Conditional probabilities, they come from the prior probabilities. This is probability of D coming from where? A.
Mm,
This is a probability of D coming from where?
B.
B. The conditional probabilities don't always add up to 1. So this is 0.1 and this is 0.04.
mhm.
And we also have what we call the joint probabilities, which are also called the intersections. When you multiply this one, because the A is down there, this is as good as what? D intersection A. When you multiply these two. When you apply these two again here, this is D intersection what? B.
B.
So multiply this by that one, what do we get? 0.04. Multiply this one and that one, what do we get? 0.024. When we add these two probabilities, we get the common letter which is there. What is the common letter?
Yeah.
What letter is common?
D.
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 So this will give us 0.
Sorry, sir.
Yes, please.
For the intersection there, what were you adding to get the 0.024?
Multiplying this one times that one. This is column A, column B, column A times column B.
Okay.
This times that, we get this. This times that, we get this. Then
Okay.
we can call this one row 1, row 2. To get the total here, it's simply row 1 plus row 2. Okay. So finally, we get what we call the prior probabilities.
Posterior.
Posterior, yes, thanks. Posterior probabilities. This is a prior and this is a posterior. The posterior should always add up to 1. So when we divide this one divided by that, it will be A given D. This letter will be down there. So this will be A over D. When we divide D intersection B over D, it will give us B given D. So what is this one divided by that? We get 0.625.
625.
This one divided by that, what we get?
0.375.
0.375. The total is giving us what?
1.
So when they ask you what is the probability of D, is 0.065, 0.064. A given D, 0.625. B given D, 0.375. These carry about 10 marks, just what we have done. Now, how do the actual questions come? The actual questions come in a manner like this. So for this particular question we're doing, and just run through this one from where it came from. Then we look at the previous test. Okay. So in the pamphlet, we have
Sorry, before you go to the question.
Hmm?
Hello?
Yes. Yes, please.
Before you go to the question, column B, my network was breaking on the conditional column. Did you say anything about the sum of these, or I missed that one on the conditional column?
This one here. When you total this plus that, we get this. We get the common letter.
Yes.
Okay. This is theorem 2. Theorem 2 simply states that if you're adding, for instance, A intersection D plus B intersection D plus C intersection D, the total will be called the probability of the common letter, which is probability of D. So here there's a D, there's a D, there's a D. So this is a probability of what? Of D. So summing them up, we titled it probability of D because this is a common letter here and there. But when you divide this one, intersection of this one divided by D, it will be A given D. If we divided this one over A, it will be D given A. The divisor is what comes down there. So you tell me, if I had probability of X
Okay.
intersection Y over the probability of Y, what will this one be? X given Y. Remember, even as we expand this one, the Y goes down first, then intersect these two. How about if we had X intersection Y over the probability of X? What does one become? Y given what?
Probability of Y given X.
Excellent. Now the question we're
X.
answering indirectly came from this pamphlet. So we're told two machines are producing the same item. Last week, machine A produced 40%. That's why I said probability of A is equal to 0.4. And the remainder came from B. So the remainder, we know that they should add up to what? 100. So the remainder is 0.6. Then we are told on average, 10% of the items produced by machine A were defective. So we said defective coming from A was what? 10%, which is 0.10. Then also 4% of the items produced by machine B were defective. So defective coming from B was what? 0.04. What is the proportion of last week which was defective? They're asking for the probability of D. If an item was selected at random, what's the probability that it was found to be defective and it came from machine A? They're asking you for the posterior for this one. They're simply asking for A given D. So what we've done is a summary of that question here. Machine A, 40%, the remainder, 60. Of those items produced by machine A, 10% were defective. Defective coming from A. Of those items produced by machine B, 4% were defective. Defective coming from B. What is the probability that the entire production had defective? So when you apply this one times that one, it will give you 4% of those ones that were defective and coming from machine A. When you apply this one and that one, it will give you defective, which is 2.4% of those items that were coming from machine B. The entire defectives is when you add this one and that one, which is 6.4%. Then they ask you, of these items that were found to be defective, what is the chance that the item came from machine A? So you simply divide this one over the total defective, which is 62.5. If they asked what is the chance that it came from machine B, you divide this one divided by that, which is the 7.5. They'll usually ask one of them. So this is how it goes. Now, in the other, are there any questions before I proceed?
Yes, I wanted to find out something.
Mhm.
Just go to where the question is.
The question is,
Yes, where the actual question is.
okay. The question is, okay, so it's here. Yes.
Okay. So if on right when it where they were saying machine A where On 10% of the items produced by machine A were defective and 4% of the items produced by machine B were defective. So when writing the probabilities, if we're to write probability of A over D, it means you'd get, it would give you the wrong answer, right?
Yes.
Or what is the difference between probability of D and A over A and A over D?
So I've simplified the language
trying
for
to
you in a
understand the
layman's
question.
language to understand
Yes.
that D given,
Mhm.
read it as defective coming from A, defective coming from B. So
Okay.
this is where it's the prior coming from. If you put
Okay.
A given D, it's like defective coming from the defective, total defectives. So you don't have this yet. You can't find this.
Okay.
Yeah.
All right. Okay. Thanks.
Okay. Any other questions?
Just to encourage the colleagues that this table is very useful in Bayes' theorem. I think I personally had challenges, but from the time I came to understand the table, I can answer any question.
Excellent. So thank you for that. It simplifies a lot of stuff because this jargon that he brings, I'm sure you saw the previous two papers and the final exam that your colleagues wrote, it was something else. Talk of the assignment, also it came in. So this simplified much of the work. So I'm glad you're appreciating this. So this is what came. I don't know whether it was in your assignment or in the previous test. So let's try this together. Suppose an item was manufactured by 3 machines, X, Y, and Z. All the 3 machines had equal capacity. Okay, so meaning that equal capacity, they were all adding up to 1. So meaning this was 1/3, 1/3, and 1/3. So if you're going to divide this, somebody might want to use 0.3, 0.3, 0.3, but probability for recurring decimals, it's best to leave it as a fraction as it is, because if you're going to have 0.3, 0.3, you're going to have 90, and the 10 will be an error. Unless you have there are 4 of them, W, X, Y, Z. 1/4 is 0.25. Those are definite numbers. So all 3 have equal capacity. It is known that percentages of defective items produced by A, X, Y, and Z is 2, 7, and 12. All the items X, Y, and Z are put into a bin. And from this bin, one is drawn at random and found to be defective. What is the probability that this item came from machine Y? So this is the same thing we're just talking about here. Prior probabilities. Then we got what? Conditional. Then we got what? Joint. Then we got what? Prior or posterior. So X, Y, and Z. What were the probabilities? 1/3, 1/3, 1/3. Then we're told that X had what? 2%. So defective. So this is a probability of X, probability of Y, probability of what? Z. So defective coming from X was 2%. Defective coming from Y was what? And defective coming from Z, we had 2, 7, and what? 12. So 0.02, 0.07, and 0.12. All right. Having found that, the joint is the intersection. Here we're going to have what? D intersection X, D intersection Y, D intersection what? Z. Whatever we're going to get there, the total will be the probability of what? The defective. Then they're asking only for one item. What is the chance that it came from Y? So in short, they're asking for Y given D. So this, I would want you to try. I'm just giving you the structure of how you get And these marks were understated. It's supposed to be even 14 marks or 10 marks, but otherwise, it's better you know what's supposed to be done. Was I a little fast there, or are we able to really try that on our own and send it over for marking? I want you to put in an effort. Please try it. I'll send it on the group so that you try as your homework. I will end here. So the first thing you do when you're given a table like that is to find the totals. So the total here is what? 9. What do we have here? 11. What do we have here? 7. And what do we have here?
13.
And the total of totals is what?
I'll
20.
be coming.
So how do we find the probability of A, B,
Baby.
X, and Y? So to find the probability of A, find the total for A, which is what? 7 over 20.
Right.
0.35. And probability of B was what?
9 out of 20.
9 out of 20, which is what? 0.45. Then X and Y.
X is 13 out of 20. Then Y is 11 out of
0.65. And Y is what?
11 over 20.
11 over 20. Get what? 0.55. Then what is A intersection B? A intersection B, where they meet, 2 out of what? 20, which is 0.1. Then A given B, where they meet is still 2, but this time not the total of everything, the total for B. B, the total is what? 9. Then A, B given A, where they meet at 2, but the total for A. What is the total for A? 7.
7.
You can convert to decimal. And if you ask A union B, it's simply the probability of A plus the probability of B minus the intersection of what? A intersection B. So with that being said, find the probability of what? X intersection Y, probability of X given Y, probability of Y given X, the probability of what? X union Y. Write that on your piece of paper quickly. And I'll ask you at random. So X intersection Y.
6 over
Once.
20 over 11.
Pardon?
6 over 11.
6 over 11. Do we agree with her?
Ah,
Yes.
no. 6
No.
over 20.
Writing.
over 20.
6 over 20, which is 0.3. Okay, how about X given Y?
That's now the 6 over 11.
6 over 11. Mhm. Next.
6/13.
6/13. Mhm. Next. Okay. So we now go to the test which the colleagues wrote on distance. I haven't shared this one. Let me share it now. So this one here, I want you to now use that knowledge to lead me to try question number 2. Okay, we're given data for promotion and qualification. So the status and academic qualification. So we're given the totals already there. I want you to try, please be objective. What is the probability? So we're given the information of the status of being promoted or not non-promoted, MBA, non-MBA, and the total. So here, what is the probability? What is the probability of the promotion after MBA has been identified? Okay. So in short, they're asking us for the probability of what? B. What's the probability of B?
It's 0.40.
Yes. How did you get that? Probability of B, the total for B over the grand total. So 0.4 over 1, which is what? 0.4. Then part B,
So that's a conditional probability of the condition that it is an MBA when a promoted employee has been chosen. So promoted given MBA.
so promoted, calculate the conditional probability that an MBA when promoted. So
When, yeah,
0.4.
A given what?
promoted.
Given B.
Yeah.
Okay. So A given B. What is A given B?
0.14 over 0.40.
0.1.
0.14 over what?
0.35.
0.4. The total for B.
Yes.
Calculate the conditional probability that it is an MBA given.
Okay.
Okay, you need to follow it closely. Then the last one here, what's the probability that a randomly promoted employee was MBA? What are they asking for? Probability of what?
MBA, probability of
A.
MBA.
Yeah,
That one was?
which is
That one was walk
Given
over.
promoted.
Yes, probability of A. All right. So at least you're able to follow through. So I've sent you the solutions here. So those of you who are in the test team, what